When we think of high-speed travel, we often look to the sky. But there's a physical ceiling to how fast a vehicle can move while tethered to the ground by traditional wheels. At high velocities, the friction between steel and track becomes a destructive force, generating heat and vibration that limits efficiency. To move faster, we don't necessarily need more horsepower. We need to change the nature of the contact itself. This is the fundamental promise of magnetic levitation, or Maglev. It is a system designed to effectively delete friction by allowing a train to glide on a cushion of air, controlled by invisible magnetic fields. The core problem with conventional rail is mechanical resistance. As a train accelerates, the energy required to overcome the rolling resistance of its wheels grows. By the time a train hits 300 kilometers per hour, the mechanical wear on the tracks becomes immense. Maglev technology circumvents this by using electromagnetic forces to lift the entire vehicle a few centimeters off the guideway. Without physical contact, the only thing slowing the train down is air resistance. This shift from mechanical engineering to electromagnetic physics allows us to reach speeds that were once reserved only for commercial aircraft. The dream of a floating train isn't new. In the early 20th century, Robert Goddard, the father of modern rocketry, envisioned a vacuum-sealed tube where cars were suspended by magnets to travel at incredible speeds. He realized that if you could remove both air and friction, the energy needed for transit would drop significantly. While we haven't quite mastered the vacuum tube on a large scale yet, the magnetic suspension part of his vision has become a reality. Today, countries like Japan, China, and Germany have spent decades refining two distinct ways to achieve this levitation. To understand how this works, we have to look at how magnets interact. We know that like poles repel and opposite poles attract. Maglev systems use this basic principle, but on a massive, precision-controlled scale. There are two primary methods used today: electromagnetic suspension, or EMS, and electrodynamic suspension, known as EDS. Both achieve the same goal, lifting a heavy train, but they go about it using different physical mechanisms. One relies on the power of attraction to pull the train up, while the other uses the power of repulsion to push it away from the track. In the German-developed EMS system, the train features arms that wrap around the guideway. Electromagnets located on these arms are attracted to the underside of the rail, pulling the train upward. This might seem counterintuitive. How do you stop the magnet from simply snapping onto the rail? The answer lies in sophisticated sensors that measure the gap thousands of times per second. Computers constantly adjust the magnetic strength to maintain a precise, constant distance of about 15 millimeters. It is a delicate, high-speed balancing act that requires incredibly fast processing to keep the ride smooth and stable. The Japanese approach, electrodynamic suspension, works differently. Instead of attraction, it uses the power of repulsion. The train is equipped with superconducting magnets, which are cooled to extremely low temperatures to allow electricity to flow with zero resistance. As the train moves quickly over coils in the track, it induces a magnetic field that pushes back against the train's magnets. This creates a powerful upward force that lifts the vehicle nearly 10 centimeters off the ground. Interestingly, an EDS train starts on rubber wheels and only begins to fly once it reaches a certain speed. Levitation is only half of the story. The train also needs to move forward. This is achieved through a linear motor. Instead of a circular motor spinning an axle, a maglev uses an unrolled motor laid out along the track. Alternating magnetic fields along the guideway pull the train's magnets from the front and push them from the back. This creates a wave of magnetic force that the train essentially surfs. By changing the frequency of these magnetic pulses, operators can control the train's speed with extreme precision, allowing for rapid acceleration and smooth, regenerative braking. The efficiency of this system is remarkable. Because there are no moving parts in the propulsion system, no gearboxes, no engines, and no friction-based brakes, the maintenance costs for the vehicles themselves are significantly lower than traditional trains. There is no metal-on-metal contact to cause wear. The train doesn't even carry its own fuel or a heavy engine. The power is supplied by the track itself. This makes the train much lighter, which in turn reduces the energy required to reach the 600 km/h mark, making it a viable alternative to short-haul domestic flights. However, the technology is so superior, why isn't it everywhere? The primary barrier is the infrastructure. Conventional trains can run on existing tracks that have been in place for a century. A maglev requires an entirely new, highly specialized guideway built to incredible tolerances. The cost of building these tracks is high, often requiring massive bridges and tunnels to keep the path as straight as possible. Furthermore, switching tracks is a complex mechanical challenge for maglevs, as the entire heavy guideway must physically move to redirect the train, unlike a simple rail switch. Despite the costs, the world is moving forward. Japan is currently building the Chuo Shinkansen, a line that will connect Tokyo and Nagoya in just 40 minutes. China is testing even faster prototypes designed to bridge the gap between rail and air travel. As our cities grow and the demand for sustainable, high-speed transit increases, the logic of the flying train becomes more compelling. By mastering the invisible forces of electromagnetism, we are moving toward a future where distance is measured not in hours, but in minutes, all while hovering a few inches above the Earth.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.